So welcome to office hours, and I'll pin our notes. Is that in focus? Okay.
Yeah,
That's
that's
perfect for
good.
me.
Great. Hey, Isaiah. All right. So let's start with whatever you want to start with. Go ahead, Elise. You were here first.
I'm pretty much just here for review and to make sure I'm ready for the test tomorrow. So I don't think I have any specific questions in general, just to go over some stuff.
Okay, Isaiah, do you have any specific questions?
Yeah. I had some questions about the homework that was not supposed to be graded.
The worksheet
Uh,
on 5, 6, and 6-1?
yes, ma'am.
All right. I've got that right in front of me. Which one would you like to start with?
I'm about to pull it up right now because I was doing it earlier and I had some questions about it.
All right. So the worksheet.
Oh, yeah, so first, um, yeah, prove the subset inclusion. Wait, no, am I tweaking? No, this is special homework 11, sorry, wrong one. This is 5.6 and 6.1. Yes,
Yeah,
okay.
it's a worksheet.
Yes, yeah,
It's
the
not
work.
to be turned in. It's
Yeah.
it's it's homework number 10
Yeah.
for um the Monday, Wednesday people, but for the Tuesday, Thursday people, it's the worksheet.
mhm.
All right.
I had a question about number two. So after finding terms D is zero, D one, D two, proving that the sequence satisfies the following recurrence relation for K for Craig equal to or greater than one.
Yep.
Um, is that a proof by inclusion? I mean, sorry, induction,
Induction?
excuse me.
No, this one actually does not have to be proven by induction. Let's do it.
Is direct proof.
It's a direct proof using the formula.
Okay.
So A, I'll assume you can do that because you didn't want. All right, so prove the sequence, and we call the sequence, D sub k or D sub n or whatever, in set brackets, satisfies this recurrence relation. Okay. And it's interesting because the indexing for the recurrence relation is for k greater than or equal to 1. And it says, oh, D sub k is going to be D sub k minus 1 plus 4. Okay.
Mm-hmm.
Well, we can see this is an arithmetic sequence with common difference 4, right?
Mm-hmm.
Because we just keep adding 4 over and over. Like if D0 is 5, and then D1 is 9 because it's 5 plus 4
Mm-hmm.
times 1, right? And
13
what's D? Yeah, 13. What's it?
and 17.
17 is D3, right?
Yeah, these are zero, these are one. Yeah, that's these are three. Yep.
Yeah. So it's an arithmetic sequence, and it really just means all this is saying is to get to term D sub k, we take the term before it and add 4. So we want to prove that. Okay? So we
Mhm.
have this formula that's given to us. This is what's given, as opposed to what we wish. This is our wish. All right? And there's two ways to do this. Hey, folks, I see we're filling up. All right, so solution one. Does it matter which side of the equation we start with as long as we can turn it into the other side of the equation?
No.
Nope. All right, the first thing to do is just notice when k is greater than or equal to 1, the given formula tells us what d sub k is. D sub k, according to the formula, because k is big enough, in fact, k is bigger than or equal to 1. This formula starts with the indexing at 0. So it certainly works for K. It says, oh, it's 5 plus 4 times what when the indexing variable is K?
Can you say it over time?
All right, so we're going to write an equation for d sub K using the given formula. We'll call this
Mhm.
equation star.
Mm-hmm.
So instead of an N, we have a K.
Mm-hmm.
So what does the formula tell us d sub K looks like?
5 plus 4, 5 plus 4 times an integer.
Yeah, but notice how the N matches the indexing number.
Mm-hmm.
So when the indexing number is K, what should we put here?
Okay.
K. And we can also use the given formula to find d sub K minus 1 because the given formula starts working at 0, and when K is at least 1, then 1 minus 1 is no smaller than 0.
Mm-hmm.
So what does that formula tell us d sub K minus 1 looks like?
5 plus 4k minus 4 is k. Ooh, yeah, k minus 1. Yeah. All right,
Yep.
cool.
So this is our wish right here. We want to prove this. We can start two ways, okay? We can start with dk. In fact, I'm just going to put this here because the solution for both of them hinges on these two equations that we got directly from the given formula.
Mm-hmm.
All right, so if we start with d sub k in our solution 1, d sub k, according to the formula, is 5 plus 4k, right?
Yeah.
This is by equation star. There was a WebAssign problem very similar, except I think it was geometric. Well, one of the things we can realize is that 5 plus 4k is equal to 5 plus 4 times k minus 1 plus 4. This is just by algebra. All I've done to 5 plus 4k is subtract 4 and then add 4 back. So I haven't changed it. I've just, added 0. Well, that is equal to d sub k minus 1 plus 4, because the d sub k minus 1 is 5 plus 4 times k minus 1. So this is by equation double star. So I had to kind of think ahead to get this one. So it might be easier to realize we're just trying to prove an equation. It doesn't really matter if we start with this side or that side, as long as we can turn it into the other side. So it
Mm-hmm.
might be easier and more natural for you to start with this side, d sub k minus 1 plus 4. Well, we know what d sub k minus 1 is. It's, did I say minus 4? I meant to say plus 4. It's 5 plus 4 times k minus 1. That's d sub k minus 1 by equation double star, and then the plus 4. Do you see that?
Yeah.
Well, what is this? This is 5 plus 4k minus 4 plus 4, which is just 5 plus 4k, and that is equal to d sub k by equation star. So you can do it either way. This
Yes.
might be easier,
Yeah, that way is a little bit easier.
right? Because you don't have to kind of like jump ahead.
Uh-huh.
Uh, this is, fine. Either way, we've proven that the equation that we wish to show is true. But in both of them, we have to use both equation star and equation double star.
Of course. I have a question. Doesn't matter. It doesn't matter when on the test. Doesn't matter which way we do it, as long
It
as
does not matter.
okay, cool.
So, I can, do you want, a do later problem?
Yeah, for sure. Yeah, I do it. We do it
I can
later.
give you two do laters. Well, maybe one, two. We'll see how much room I've got here. I'll call this 2 prime. Say the formula for, I don't know, A sub n is that A sub n equals 4 times 3 to the n for n greater than or equal to 0. So that's given.
Mhm.
Prove for k greater than or equal to 1 that d sub k is equal to 3 times d sub k minus 1. That's our wish. So this is a geometric sequence. Do you see what the common ratio is?
Yeah.
We're multiplying over and over and over again by what value?
3.
Uh-huh. And so that makes sense that d sub k would be 3 times the prior term.
Mm-hmm.
So you can practice the algebra for that. And you can just make up another one of these for yourself. All right. Good. Is that good?
Yeah, that's good.
All right. Next question. Hi, everybody. I'm so glad to see. Boy, I've never had so many people in office hours. This is wonderful.
Yeah.
We are looking at the worksheet for section 5, 6, and 6.1. For those of you who have your test tomorrow, that was a worksheet. For those of you who have your test on Monday, that was homework 10 that you turned in today. So right now we're working on that worksheet / homework 10. So if you're in Monday, Wednesday, it's the same as the worksheet for Tuesday, Thursday. All right, next question. Does anybody have any other questions on the worksheet or that homework 10? Of course, in class today, we looked at special homework 10, before we started the set worksheet. Do you want me to share my screen and show the worksheet, or does anybody need me to share the screen? I got a chat here. Let's see. When you put equation star, is that indicating that it is by the induction? Elise, that's a great question. We actually don't even use induction at all in this problem. We are given a formula for the sequence, and we're proving that this sequence is actually recursively defined with this recurrence relation. We never actually used induction. We simply used, see, we want to prove something about a relationship between the term d sub k and the term d sub k minus 1 right before it. We don't need, you could prove this with induction, but if you started to prove it by induction, you would realize I don't even need induction. We're just using the formula. We're using the given formula right here and just saying, okay, d sub k, according to this formula, is 5 plus 4k. It's a k instead of an n. So it kind of seems like induction in some sense. There's a lot of common elements here. We're dealing with indexing numbers, and we're dealing with k and k minus 1, or we could say, I could rewrite this and say d sub k plus 1 equals d sub k plus 4. So in some sense, we're looking at a step from k minus 1 to k. The same formula tells us what d sub k minus 1 looks like. See here, the n is k minus 1. Well, you just put in k minus 1 for the n here. So these two equations allow us to establish that this recurrence relation is really true. And the easiest way to do it is to start on the low side. Start on the side that has the prior term, d sub k minus 1 plus 4, Now, this is the right-hand side of this equation, and we can easily turn it into the left-hand side of the equation, showing that those sides are equal by just using these two e equations that we got by simply applying the formula twice. Does that make sense, Elise? We plug in for d sub k minus 1. That's what it looks like right here. And then, of course, there's a plus 4 there. And then we just go ahead and see what that looks like. Oh, the minus 4 and the plus 4 go away. And this really turns into 5 plus 4k. But that is what the formula tells us d sub k looks like. So yeah, it's funny that you asked that because the first time I was teaching this material years ago, I thought I needed to use induction too. And then I realized, no, man, we don't need induction for this. We can just use the formula twice. But of course, we do have proof by mathematical induction on the test, number 3 for everybody. So we can talk about proof by mathematical induction, or we can talk about more worksheet problems, whatever you want to do. So y'all need to tell me.
If no one else has a question, I was just gonna say, can we continue? Can we talk about union and intersects?
Sure.
And
And there's a typo in the worksheet for part B. I accidentally changed I equal 0 to I equal 1 in the third and fourth parts of part B. That was an accident. But, do you need to, would you like to look at A?
yeah, I'd like to look at A.
All right, so we have been given that A sub k is an interval of the real line that looks like this: minus 1 over k, comma, 1 plus 1 over k. Okay, so that's what that interval looks like. And if we want to find all those sets and those unions and intersections, it helps to go ahead and find A1, A2, A3, and A4, right? Because those are the ones that are involved in those unions and intersections for the first two parts, right? So let's go ahead and find those. So what does A1 look like? Well, K is 1, right? This is when K is 1. So let's just put a 1 in everywhere we see a K. So tell me what this number becomes. It's minus 1 minus,
minus one.
that'll turn into a 1.
Yeah, negative
And
one.
then here we got 1 plus
Two.
1 over 1, right? And you're right. This just turns into minus 1. This just turns into plus 1. So what is this interval really?
Negative two, two.
And then we want to use soft brackets because that's what we're told. That means we're not including the negative 2 or the 2, right?
Mm-hmm.
We're just sneaking up on them as close as we want. So when K is 2, let's take a look. We've got minus 1 over 2, right? And then here we've got 1 plus 1 over 2. Well, minus 1 minus a half is minus 3 halves. And then this, of course, is positive 3 halves. I'm going to use fractions because they're more exact when you have like thirds and stuff. All right, so can you tell me what A3 is going to look like?
Plus three, K equals two, A2, A3. Negative one, minus
Might be easier to find this one. What's 1 plus a third?
uh,
3/3 plus 1/3.
4/3.
Yeah. And then this one will be symmetric. It'll be minus 4/3. All right. Got one more. And then we'll draw a picture so we can really see what's going on here. Can you Tell me what 1 + 1/4 is.
It's gonna be 5/4.
Yeah. So it helps to draw a picture, right? So let's
Yeah.
just draw a picture so we can see how these look relative to one another, okay? I'm gonna pull the two out further than it's supposed to be, just so we have a little more room, because all the action's gonna happen between 1 and 2. Do you see that?
Mm-hmm.
I mean, all this interesting stuff really happens, in here. So I'll make it a little bigger than it's supposed to be between negative. All right, so the first A1 goes from -2 to 2, but we're not including the endpoints. So we can draw that in with blue. And I know this takes time, but if you do it a few times, you get better at it. See, that's A1 right there. Now let's draw A2 in red. It goes from -3/2. Well, that's right, but smack dab between -1 and -2, isn't it?
Yeah.
And +3/2 is smack dab between 1 and 2. So A2, look at that. It's nested inside A1, isn't it?
Yeah.
It lies completely inside A1. These actually happen to be nested sets. It makes them kind of interesting. So A3 goes from -4/3. So I have to kind of split this into thirds. So here's -4/3. And I'm splitting this into uh, uh, thirds and +4/3. And so it's sitting right in here. This was A2. This is A3. And I'll draw A4 up above. A4 goes from so 4, so half of a half. It's going to be like right there. These get closer and closer together, these dealy bobs. Anyway, so it's the one that's right. It's the smallest one. It's right in there. All right. So at least we can see what's going on. And you can see that as K gets bigger, these sets just get closer and closer and closer and closer to -1 and 1. But they never actually touch -1 and 1. See what I
Mm-hmm.
mean? They're always a tiny bit, a little bit more, but they're always like a tiny bit outside of -1 and 1. See?
Yeah.
So when we start to look for the union from K equals 1 to 4 of A sub K, well, we're looking at -2 to 2 union. So what does the union operator mean in
Uh,
set land?
or
Or so we're looking for elements that are in A1 or in A2 or in A3 or in A4. But look, A2 is contained in A1 and so is A3 and so is A4. So what's the union of all these?
I don't know.
All right. So we're looking for elements, real numbers X, that are in this A1
Mm-hmm.
or in the red one or in the green one or in the other blue one, anything that's in any of these.
Mm-hmm.
So how far to the left do we go in any of these?
-2.
Yeah. And how far to the right do we go?
2.
And that's the fact of the matter is A1 is, or you can write it this way, is the union of all of those because all these other ones are contained inside A1. Does that make sense?
Yeah, that makes sense.
All right, now let's look at the intersection. Now, what does the intersection operator mean in setland?
And
It's and. So we want x's that are in -2, comma 2, and in -3/2 to 3/2, and the x also has to be in -4/3 to 4/3, and also has to be in -5/4 to 5/4. So the only x's that will be in this intersection have to be in A1, and they have to be in A2, and they have to be in A3, and they have to be in A4. So what x's are in all four of those?
-5 fourths
Yeah,
or ace of four.
yeah. -5/4 to 5/4. Or you could just write a sub 4. Because only those elements that are right here in the middle are in all four of those.
Uh-huh.
All right, so now let's up the ante and let's imagine that we are going to take the union starting with k equals 1, but we're just going to keep going forever. Well, let's just think about what happens if we try to keep going forever. See, A1 was the biggest one, right?
Uh-huh.
A2 was inside that. A3 was inside that. A4 was inside that. A5 will be inside that. A6 will be inside that. A7, all of them, no matter how big K is, they're all going to be inside the one that was the biggest one to begin with.
Uh-huh.
So what is that union?
I have a question.
Uh-huh.
They'll get I guess infinitely smaller, but they will never touch one, correct? Or they won't touch -1 or one, right?
Yeah, they'll always be a little to the outside. But for the union, we're really, this is the biggest one of all.
They're always going to be inside
They're always going to be in that. So it's the same deal as it was when we were only unioning up four of them. It doesn't help our cause to union up with more because they're not giving us any more elements because they're inside.
Yeah,
So what's the answer here?
it'd be ace of one.
That's right. I like that you're calling it ace of one because that's quicker to write. Now let's think about it in the other direction. Let's imagine that we're going to keep intersecting and keep intersecting forever. I kind of hate that this doesn't all fit on one page. Oh well, life is not perfect. So if we keep intersecting and just keep on doing it, let me put this down so we can look at the picture, all right? These sets just keep getting smaller and smaller and smaller, but you have hit on a key fact. No matter how far we go with this game of listing these, yeah, they get smaller and smaller. But you really hit on it when you were like, but -1 is always going to be inside of any of these, and 1 is always going to be in each of these, no matter how close they sneak up from the outside. They're never going to hit -1 or 1. They're going to include -1 and 1 as elements. See how -1 is smack dab inside, but all of these?
Mm-hmm.
-1 is going to be in every single one of them. Because no matter how tiny that distance is, there's still some distance between -1 and the left bound. And there's still some distance between 1 and the right bound, no matter how big K gets. So when you think about it, what do you think is going to be in every single one of these, no matter how far out we go? On the left, what number for sure is going to always wind up being inside?
Uh, Ace of four.
Okay. Well, we've only drawn four of them. Ace of four was from negative 5/4 to 5/4, but ace of five is going to be from negative 6/5 to 6/5. It's not going to have
So would it
these,
be
it's not
K
going to
plus
have
one?
these elements. So what did you say?
I say K plus one.
Um,
Like
well,
I'm thinking like it'll never hit. Like it's always gonna be inside. Like even
negative
at that.
one is always going to be on the inside.
Yeah.
But any other real number that is to the left of negative one, like if you pick a real number that's like really close to negative one, like here, let's say that's negative uh 1,001 over 1,000.
Mm-hmm.
There's still going to be a k plus one that's bigger, k plus, ace of k, this would be what? A sub uh 1,000. Well, a sub, you know, 2,000 is going to, you know, not have this number in it because it's going to be sneaking up closer. See,
Mm-hmm.
so you can't pick any of these numbers that are actually to the left of negative one and be guaranteed that those numbers would be um, in all of these sets. That's just not going to happen because you can always find an indexing number where the left bound is to the right of any number you try to say is for sure in all of the A sub k's, you see. But
Mm-hmm.
negative one is going to be in all of them. See what I mean? The left bound is always going to be a little bit to the left of negative one. So the only number on that left side that is going to be in all of these, no matter how big the indexing number gets, is negative one. So actually, negative one is in all of them. And then it's the same idea over to the right side at plus one. You can sneak up closer and closer to plus one, but every single set's going to have the plus one in it. But there is no number bigger than plus one that you could be guaranteed would be in all of the sets because there'll be something way out here that sneaks inside. Does that make sense?
That makes perfect sense. I see what you're saying.
Oh, I'm so glad. That's sort of a hard concept to explain, but once you see it,
Yeah,
uh,
when you see it, you see it, you
you
understand it.
see it. Yeah. Okay, that was a great question.
So I got a question about
Yeah.
that.
Hey, hey,
So for
Steve.
the hey, yeah, how you?
Good.
Yeah. So for the like the start, like before you did the number line. So did you go all the way to ace K4 because on the
Oh,
questions
look,
that's
I meant to
the
say four here, didn't I?
yeah. But
Hey, you can email me for some credit. Okay, what else?
uh, so did you stop at four because that was like the most on the questions?
That's
Ye-
exactly why I stopped
Oh, all
there.
right.
I just didn't want, I
Uh-huh.
wanted to see enough that I could actually get these
Yeah.
values to get the actual answers.
Uh-huh.
But it's enough that we see what's going
Yeah.
on. But there's no way I'm going to sit here and draw 100 of them.
Right.
But if we get the notion underneath our skin here, we realize taking the union of more and more doesn't do anything for us because the biggest set was at the
It's
very beginning, right?
yeah.
And it contained all the other ones.
Right.
But it does help to kind of
Mm-hmm.
imagine in your mind what's going on if we did keep going. These numbers just sneak up on negative one and they sneak up on one on the right. But you can always, get something that won't have a particular value because the next set wouldn't have those ending values. See what I mean?
Right.
but -1 will be in every single
And
one of them.
right.
And +1 will be in every single one of them. Look
Mm-hmm.
at you all learning about limits by accident and everything.
Right.
No, on purpose. All right, great. So, like I said, there was a typo on 3B.
Mm-hmm.
For those of, it's, but you can just either correct the typo or you can work it the way that it said. Um, I was copying and pasting, but this is a very different kind of situation. It's worth looking at.
Yeah, I was about to say, could we do this one together?
Sure, let's do it. So let's first find well, how many do we need to find? Oh,
3,
B0. We're
0
gonna
to
find
3.
B0, B1, B2, and B3.
Yeah.
All right, so first find, B0 through B3. Okay, so you help me. When I is 0, we're
So
just
it's
gonna
gonna
put a
be
0
a
in,
0,
2,
0, and 0 plus 1.
which is 1.
Yeah, 1. Yeah.
Notice how this set
It
includes,
includes, yeah, and that
but
excludes.
doesn't. Exactly. All right, you got it. What's B1 gonna be?
So that's 1
Uh-huh.
and 2.
Thank you. Same kinds of brackets and soft brackets, right? And
Yeah.
B2,
So that's gonna be 2 and 3,
all right. And B3.
3 and 4.
Now this one's kind of very different to draw. Let's draw this one. In fact, we don't need, it's not nearly as hard. All right. So here's our 0. 1. We'll draw it 2. We got to go up to 4, right?
Yeah.
And we can just imagine we might, eventually. All right, so B0 includes 0, does not include 1, but gets as close to 1 as we want, and includes everything in between, right?
Yeah.
Don't forget, these are real intervals, and it's not just the integers.
Hmm.
There's B0, right?
Yeah.
Now check out what happens. B1 does include the 1, does not include the 2, includes everything in between. So do you see the relationship between B0 and B1?
Hmm.
Can you tell
So
me, are they disjoint? Let's review disjoint. They're disjoint if their intersection is empty, if they have nothing in common.
oh yeah, I would say that this joint because B0 does not include 1,
Uh-huh.
while B1 includes 1.
That's right. And everything in B0 is
Mm.
less than 1,
Yeah.
and everything in B1 is 1 or bigger. So they've got nothing in common.
Yeah.
So we can play that game. See how B2 starts with 2, does not include 3, but sneaks up on 3 as close as you like. There is actually no largest element of any of these little subsets. There's an upper bound, but there's no largest element. The minute you tell me you've picked the largest element in B2,
Hmm.
whatever element you pick, I'll get my microscope out and I'll pick an element that's bigger. So it's kind of a fun kind of concept thing.
Hmm.
Just to kind of, it's just like a game, it's like a little mind game. And there's B3. All right, so we've drawn B0, 1, 2, and 3. See how different that is?
Yeah, that's way different.
All right. And again, sorry about the typos, but one didn't have a typo. I meant to say the union from I equals 0 to 3 of BI. Maybe I shouldn't put this here. Maybe I should put this where the typos actually occur. Okay. So help me with this. We are talking about from 0 to 1, don't include the 1,
Yeah,
union.
yeah. 1 to 2.
Mm-hmm.
Don't go to 2 to
Right.
3 and 3 to 4.
So when we really look at that, and we want to express that, can we express that as a single interval?
Yeah, would it be 0 to 4,
Uh,
but include
uh,
0 and not 4?
exactly. Because these don't share any elements at these integer points, but
Hmm.
but there's a continuous flow,
Yeah,
and we're not missing anything.
yeah.
All right. So oh, my hand is cramping up. Look at that. It's going crazy. All right.
Sorry.
Oh, it's all right. I'm getting old. I'll take some vitamin C tonight. All right, now let's think about intersecting them. Now this is a big intersection. We got to find elements in the reals that are in
0 to 1,
and in
1 to 2, and
and in
2 to 3,
and that any X that comes out of this game has to be in also that 3,
3,
4.
and 4.
So what X's are in this and in this and in this and in this?
Um, is it gonna be the same? Is it's not, but
This is a very different kind of operator. This is our
mhm.
OR operator. Any X that's in here, or in here, or in there, or in B3, any of those elements that are in B0 or B1 or B2 or B3 landed in our answer.
Yeah,
But now we're looking for an X that is in B0 and it's got to be in B1 and it's got to be in B2 and it's got to be in B3. Is there any X that is in all 4 of those?
Nah,
no,
it's just joint. So like, doesn't
no.
yeah.
Yeah, they're pairwise disjoint sets. Like,
Oh,
see, haha, snuck up
yeah.
on you, yeah?
Mhm.
All right. Now listen, here's the typo. I meant to say the union from I wrote 1. I don't care whether you keep it at 1 or you go ahead and change it to what I meant, 0. But the point is, let's just play this game out to infinity. So, it's this one, union this one, union this one, union this one, keep on
Oh,
going
yeah.
forever. What's that going to be?
Yeah. So is it gonna be 0 to infinity?
It is. Include the 0. And of course, infinity is not a number, it's an
Yeah, so it's gonna
idea.
be
So
yeah.
we don't ever use a square bracket
Yeah.
with infinity or not. And
Mhm.
now if we take the intersection, I'll go ahead and change it to 0. I'm not going to change our answer. It does here. It actually does change the answer here because otherwise we would have been
And
starting with this one, right?
yeah.
I apologize for that. But if I'd sent Jonathan my tech file, he might have been able to repair it and send it back to me.
Next time.
I'll get those to you sometime here. I'm so sorry. It's been a hell of a week. Oops, did I say that on camera? Okay. Now let me ask you the question. There was nothing in the intersection from 0 to 3 of the B sub I for my equals,
Yeah.
right?
So
Does
I
does
get it.
does does it help to have to intersect with even more?
No, so it's gonna be the
No.
same thing.
Yeah, it makes it worse.
Yeah.
Intersecting with more and more sets just compounds the restrictions.
Right.
And you're right, Stephen. It was -2 to 2. We got a good group in here. Abdul's in the room. Of course, Isaiah, Shakemi's here. Rebecca's here. That's awesome. Of course, Stephen's here. This is great. All right, so that is that one. So are we good to go
So for
with
the
that?
last question, right? It says all the sets in collection C, like pairwise this. Do we just write
Oh,
yes or
yeah, yeah,
no?
yeah. Are they?
So for this one, it's yeah, it's joint.
Yeah, the collection, if we start with, whether we start with B0, I'm good. I start with
These are
B0, B2, dot, 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 pairwise disjoint. Absolutely. Because if you take any
any
two
two
of
point.
them,
Mhm.
right?
Mhm.
BI intersect B sub K is empty if I is not the same indexing variable as K. Hey, Tito's here. Does that make sense?
Yeah.
Like we have
I
to
got
say I is not equal to K because otherwise we might be intersecting B2 with B2 and that's not empty. It's all a B2 and that's got a
yeah, that's right.
number of numbers in it. So the whole thing about pairwise disjoint is saying if you take any two different ones and intersect them,
Mhm.
you know,
Yeah.
and WebAssign falls down. WebAssign is not the way that they worded the problems about pairwise disjointness and stuff and WebAssign, they could have done a little bit better job because they go to an extreme there. But anyway, that's why we're doing this. Okay, is that okay? Can I
Yeah.
we move on?
Mm-hmm.
All right. All right, so right now, folks, we're looking at the worksheet 5662, which turned into that's actually a homework assignment for Monday, Wednesday. They turned
Can
into
I see the last part one more time
Oh,
on
of
the
course.
fourth?
Yeah, thanks for asking. And I will post these, but it takes a little while to get
All right.
stuff all up.
All right, thank you. I got it.
You got it? Okay. All right, next question. Do we want to stick with the worksheet? Which is fine with me. I'm asking y'all.
I had a miscellaneous notation question because I feel like I get myself in trouble with this kind of thing.
Okay.
So I'm looking in the book in section 5.1, just as an example of where this came up. I'm looking at question, like for example, 10.
Uh-huh.
Right. So you have an alternating series, -1, 1, -1, 1. And the prompt is give a like an explicit formula for that. So I wrote to myself, a sub n equals -1 quantity to the n. And then the next part, for all n that are in Z, or n is greater than or equal to 1. The notation question I wanted to ask, right? When we're doing sets, sometimes, right, we have this little vertical bar. Sometimes, like when we were dealing with
like a descriptive such that.
Exactly, yeah. Sometimes we were using commas to do that. So the thing I was doing in my notes for myself is just the upside down A for all, and then just n element in the mathy Z,
Yeah,
comma, n greater than or equal to 1.
I'll accept that.
Gotcha. That seemed like the sort of standard way, or is that an
It
idiosyncratic way?
probably is more standard than not, to be honest. I tend to, say I'm a little wordier maybe sometimes than I need to be, but that's absolutely fine.
Okay. Thanks a bunch.
Of course. Other questions?
I had a question, but we can keep working on the worksheet, but after, can we go over proof by induction, please?
We certainly can. And we've got a nice long office hour tonight, so we should not run out of time. So let's just go right back now to the worksheet. We've just worked through 2 and 3. We skipped 1 because it's just not that difficult. It's your basic geometric sequence. We've studied those. Does anybody have questions on problems beyond problem 3 on the worksheet? And again, if you're in Monday, Wednesday, this was homework 10 that you turned in today. I'm leaving it up to you.
Can we do 4?
Sure.
Yeah.
All right. So 4 is talking about partition. So let's just recall a collection. It doesn't have to start with the indexing at 1, but it could. I don't want to get into using a variable to initiate my indexing for my collection. So I'm going to be lazy and just say a collection A1, A2, dot, 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 up to A sub n of subsets of a set A. So each of these A sub i's is a subset of some, uber set A, some big set A, is a partition or forms, their wording forms is probably better, but the key phrase, it's a partition of A. You might say constitutes a partition of A if 3 things happen. Each of these A sub i's has at least one element in it. None of them are empty. This is for all I. One, I'll say I greater than or equal. Well, this is a bounded, a collection of, I'm sorry, I didn't, tired. All right, for all I, one less than or equal to I less than or n. Just understand, you can form an infinite partition, okay? Two, they're pairwise disjoint. AI intersect AJ is empty whenever I is not equal to J, and I could go ahead and say that the I's and the J's are between 1 and N, and I'm too lazy to do that. And then the last thing is that if we take the union of all of these A sub I's, so here I do want to be careful. So I starts at 1 and goes to N. When you union all these up, it gives you the big set A back. Okay, so these are the three properties of a partition. Each of these subsets is non-empty. None of them have anything in common with any of the others, so they're pairwise disjoint. And the union of all of them is the big set A. So you can think of it like this. Here's A, and so, maybe A1 is a subset, and here's A2 and A3, dot, 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 and then, A sub n. The point is they're disjoint from each other, but when you union them together, you get A. And we don't want an empty set in this game because then where do you stop that? You would just, you just put a bunch of empty sets for no good reason, maybe. So we're given a finite set A. It's just got the alphabet letters A, B, C, D, E, F, G, and H. And we're given some collections. So C1 is, well, A1 is the set containing A, B, C, and D. A2 is the set containing E, F, and G. And A3 is the set that just contains H. So that's our first collection, okay? This is I'm just writing it a little bit quicker. A1, this is A2, and this is A3. And the question is it a partition of A? Well, let's just check. Let's check. Is each of these non-empty? Sure. A1 is not empty, because little a's in it. E is an element of A2, so it's not empty. H is an element of A3, so it's not empty. And I guess I can put little a in set A1. So they're all not empty. That's the easiest thing to check. You can just do it by inspection. What about pairwise disjoint? Well, what does A1 intersect A2? What does A1 intersect A3? And what does A2 intersect A3? There's three pairs to check, right? So what does A1 intersect A2? Who asked for this question?
It was me,
Who is me?
Steven.
Steven. All right.
Mhm.
So do A1 and A2 have any elements in common?
No.
So their intersection is empty.
Yeah.
So far, so good. What about
Mhm.
A1 intersect A3?
It's the same thing. It's empty.
And what about A2 intersect A3?
I'm saying.
All right. So far, this checked out and this checked out. And the third property says if we take the union from I equals 1 to 3 of the A sub I. In other words, we're taking A1, union A2, union A3. When we union these up, do we get A back?
Yeah.
Yep.
Mhm.
Because every element in A appears in exactly one of these non-empty sets. See, that's the way you could say it, prose style. You could say a collection is a partition if every element in the partitioned set, namely A, appears exactly once
Mhm.
in one of the non-empty subsets. So it's a partition. So yes, C1 is a partition of A. All right, what about C2? So you get the game now, right?
Yeah.
All right, so C2 has A1 and A2 in it.
Yeah.
So A1 has what? A,
A,
E,
E, G,
thank you, help me. And
okay.
A2 has,
B, C, D, and F.
all right. Well, that's up, yeah, okay. So we got A1 and A2. All
Yeah.
right, so let's check. A1 is not empty,
Yeah.
right? Because it's got an element.
Okay.
What about A2?
Yeah, it's not empty too.
Give me an
But,
element.
B.
B is an element of A2, so A2 is not equal to the empty set. So check, you know. Pairwise disjointness. We only have to check one pair because there's only one pair. What is A1 intersect A2?
Um, there's there's no common element, so there's no intersection.
So the empty set,
It's empty set.
right? There's a kind of a little difference between nothing and an empty set.
Empty
The
set,
empty set's
yeah.
like the bag, you know?
Right.
The bag with
The
nothing in there.
empty, yeah.
All right, now we're going to check property 3. If we take the union from I equals, well, it's only 2, 1 to 2 of the A sub I. So we're looking at A1 union A2. What is in that union? Let's just go ahead and write it. A's in there. Let's do it alphabetically. What else is in there?
B,
B is in there. Keep going.
C,
Uh-huh.
D,
Uh-huh.
F.
What about E?
Oh, E, yeah, E,
All right. E, I'm just going to check them
yeah,
alphabetically.
F,
Uh-huh.
and G.
All right. And is that equal to A?
No,
That's right. We're
because
missing.
there's no H.
Yeah, it's not equal to A. You know, H is missing. So, whereas the first 2 checked out, the third property fails. So the answer is a big fat no. Property 2 failed.
Okay, so if this question comes to the test, do we have to like put it in the same order that you put like
No, it doesn't matter what
yeah?
order as long as you check all 3 properties.
Oh, so we just gotta like actually write that it failed this property and like
Yeah, I'm gonna, you
like
know
if
what
it
I'm gonna
fails
give
any
you?
Mhm.
I'm gonna give you this part.
Oh, all right, all right.
I'm gonna give this to you, all right? Just
Mhm.
because, you know,
Yeah.
so I'll set it up and I'll tell you, I'll remind you the definition of partition, and then I'll give you some sets and ask you to figure it out. I'll probably ask you to check each of the 3 properties because I want to make sure you know how to check the 3 properties. And there's no guarantee the sets are going to look like this because we got all kinds of sets we've played with, including intervals. Nothing's keeping me from giving you a set of intervals and asking you if that collection is a partition of some subset of the reals or the reals or something.
Mhm.
Okay?
Yeah.
All right. So, I mean, you know, keep, just try to absorb the basic understanding of the different concepts, and then you should be able to put 2 and 2
Okay.
together.
All right.
Most of the questions will look almost exactly like questions you've seen before, but you know, there'll be a question, you know, separator question or 2 where you have to put together ideas from
Yeah.
sort of different parts of our studies and show that you can use those ideas in tandem with one
Mhm.
another. All right. Uh, um, all right. So what's next?
See, so it's
Oh,
but that's pretty much the same thing. So,
yeah,
but
we
we
don't
can
need to do
still
it.
yeah.
I
So we
mean, you
can
can see which property fails, can't you?
yeah.
All right. All right. Yeah, yeah. Yeah, the third one is not because I think which property does the third one fail?
Oh, let me just go real quick. The uh
Oh, yeah. Oh, do you need to see the definition of
yeah, can I see that again?
yeah, yeah.
Sure.
So clearly it passes non-empty, right?
Yeah, it's not,
A1, A2,
yeah.
yeah, they're not empty. Okay, so keep going.
It fails the second one
It does. Why?
because the intersection of A1, A2, and A3 is not an empty set.
All right, now that's interesting. The intersection of A1, A2, and A3 is empty, but that's not what pairwise disjoint requires. See, that's where
Oh,
WebAssign falls down because I need to write the author, actually the publisher, about that. Let's go ahead and look at 4.3. A1 has A, B, C, D. A2 has E, F, G, and A3 has G and H. Okay, what property 2 says is pairwise disjoint. That means if you take any
any two.
two of them at a time, which is not as hard to satisfy as something being in all three. It's it can fail. You see, this fails, right? Because A2 intersect A3 has G in it. That's not empty. So this fails, right? But if you tried to see if A1 intersect A2 intersect A3 is empty, it actually is empty.
Oh,
There
yeah.
is no
A,
element that's in all three of them, but that's not what pairwise disjointness says. So pairwise disjointness is not as restrictive as taking the intersection of all of them. Okay. I hope I said that right. But the point is, you don't have to find an element that's in all three. You just need to find two sets.
so if we, so okay, for example, if we use A1 and A2, it will fail too, but it will not. Oh, never mind, never mind.
I know. See, I is 2.
Mhm.
We can call J 3. These indexing numbers aren't equal, but
Oh,
A2 intersect A3 is not empty, so they're not pairwise disjoint. All three of them have an empty intersection if you tried to find something that was in all three of them. You could, that looks good, but taking two at a time, it pairwise, the disjoint property fails. Okay?
I can do it.
All right. Next question, folks. We're still working on the worksheet 5.6, 6.1, or homework 10 if you're in Monday, Wednesday. Do we need to do 5, or can folks pretty much understand that you can draw a number line and just order up all those numbers and figure it out? Sometimes a union or intersect, does anybody need to see number 5? We can work, a couple of those if you need it. No?
Yeah, sure.
Yeah, I was gonna say specifically D.
D?
Yeah, from number 5.
Okay, so our universe is the real line, okay? And D asks us to find square bracket -3, comma, what is it, 5.21?
Yeah.
Complement, soft bracket there. You know the reason I use those funky numbers? Because if I just used integers or whatever, then students started getting the idea that the real numbers are only integers. So let's draw a number line. Drawing a picture can really help. All right, so here's, I don't know, 0, 1, 2, 3, 4, 5, 6. So 5.21 is like there, right? Close enough. It's a fifth of the way, right? Between 5 and 6. And -1, -2. All right, so I picked -3 for the left bound. All right, so the set we're looking at is everything, including -3, and then to the right of -3, up to, but not including the rational number 521 100ths, right? I did pick a rational number. I could have picked pi. In fact, I changed it. This worksheet used to have pi in it. Anyway, that's the set. We want the complement. Now, do you know what the complement of the set is?
No.
All right, well, you need to. All right, let's
Yeah.
just draw a little Venn diagram.
Got the notation.
If we have a universal set, and here's a set A that's a subset, A complement is everything outside of A. The complement operator is sort of like the negation operator. It's everything that's not in here, okay?
Mm-hmm.
Well, let's take a look. Let's look to a bunch of these real numbers to the left of -3. They're not in there, right?
Yeah.
All right, so let's do those. Sorry if you're red-green colorblind. This is red, but now we got to deal with the -3. Is the -3 in the complement, or is it in the original set? You can't be in both. It's -3 is either in this original set or it's going to not be in it, in which case it is in the complement.
I would say it's not in the complement. It's included in the regular set. It's in the
That's
set.
right. So the
Um,
complement sneaks up on -3 but never reaches it. Okay. Now let's look on the other side because there's a bunch of real numbers out here that are not in that set. So these are in the complement. What about 5.21? Where does it go?
It goes outside because wait, it goes.
Is it in the complement or
I say it's in the complement.
you're right, because it's not in the
It's
original
not in the
set.
original. Yeah.
So our answer has to be written as a union because there are some x's over here. There are x's over here. So the complement set is any x that is over here on the left or over here on the right.
Mm-hmm.
So -3, comma 5.21 soft bracket complement is, how do we express these over here? We're using an interval. How do we express going to the left forever?
Minus infinite.
Uh-huh. Minus infinity, comma, then what?
It would just be
We're going to stop here. So what do we put? Still the -3, but are we going to include the -3 in the complement?
no.
No, because it was included in the original.
Yeah.
Okay, so x's that are over here, which we've written here, or there's nothing in the intersection of these two. There are no x's that are in both, so you use a union here. All right, now we want to talk about the x's that are on this side of the original set. So these are in the complement. So tell me what to write.
You 5.21 with a closed bracket with a closed bracket,
Uh-huh.
and then infinity on the right side.
Uh-huh. And we never use the square bracket with infinity because it's not a number, it's an idea.
Mm-hmm.
Is that good, Isaiah?
That's perfect. Yeah.
So that's a good one to go through. All right. Does anybody need to see more from number 5 on the worksheet, or are you feeling like you can carefully think through? It's really the endpoints that you have to think through. Plus, you, of course, need to know the definitions of union, intersection, set difference, and set complement. You do have to know those, right?
I have a question when it comes to the notation of minus. Minus is everything included. I forget.
All right, let's talk about set difference.
Yeah, we can talk about set differences.
Let's review set difference. And I'm telling you, at 9:15, we're gonna take a 3-minute break, and then we're gonna spend the rest of the time talking about induction and other kinds of things, okay? Because I think our induction discussion might, be more extensive than we might imagine. All right, set difference. Okay, here we go. Let A and B be, these are subsets of a universal set, okay? So A minus B is defined to be x's that are in A such that X is not in B. Now, that's not the only way to write that definition. So I can hear Jonathan thinking right now. So or you could define it, X is in the universe such that X is in A and X is not in B. Algorithmically, if we want to actually find A minus B, start with all of A, subtract any X that are in B as well. So if we just look at a little finite example about set difference, if we have, the universe is, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and A is the evens, or maybe the odds. Let's make it the odds. 1, 3, 5, 7, 9. And B is 1, 2, 3, 4, 5. Can you find A minus B and find B minus A? All right. So A minus B is literally start with A and subtract away from A any of those elements that are in B, because we want the grand final answer to be elements that are in A, but were not in B. So let's start with the first element of A, 1. Can we keep it or do we throw it away?
Oh, but what did you say right before that? I was writing.
All right, we want to find A minus B.
Yeah.
So we want to find the X's that are in A, but not in B, and not in B.
Mm-hmm.
So the algorithm says start with all of A. So here's all of A. And we're going to subtract any X's that are also here in B. We want to get rid of these.
Yeah.
So we look at the elements of A one by one and we figure out, do we keep it or do we throw it away because it's in B? So
Okay, cool.
first element is 1. Do we keep it or toss it?
Toss it.
3.
Toss it.
Great. 5.
Toss it.
7.
Keep it.
9.
Keep it.
I'm liking it. And don't even worry about the 2 and the 4 because they weren't even over here in A to begin with, so it doesn't even matter. They don't even, it doesn't even matter that they're in B because we're only keeping stuff that started, elements that started out in A. Now let's find B minus A. All right, here we go.
Mm-hmm.
What's going to go into B minus A? You tell me.
Throw out 1, keep 2, throw out 3, keep 4, throw out 5, keep 7, keep 9.
We can't keep 7 and keep
Oh
9
yeah, because they're
because
not
they
even in
weren't in
vacuum.
B.
For sure.
Yeah,
Because in
right.
the first place, you can't subtract something from it's not even there.
All right, so if we are going to look back at the worksheet number 5C, we are asked to start with the interval of all the real numbers from -3 to 5.21, not including 5.21, and we're going to subtract away closed interval 1.24 to 2.43 open. All right, so I'm going to take a little break, but while I take the break, I'm going to put this on pause, but you all can talk to each other. Please remind me when I get back to start the recording again, okay?
Mhm.
Or I can keep the recording going while you talk to each other. But, draw a picture, line up these numbers in order, try to figure out what you're keeping and what you're not, okay? I'm going to take a little break and then we're coming back and we're going to work on induction. Did y'all figure it out?
I think I did, but
What do you think the answer is?
I think so. To start off, I'm kind of like looking at what I'm actually doing.
That's always a good idea.
-3, uh, in 5.21, uh, is everything including -3 and not excluding 5.21. Um, and then we're
We're
checking to
starting with
see,
these.
and then in the inside of that, uh, we're trying to check if anything in -3 to 5.21 matches within one, including 1.24 and excluding
1, 2,
2.43.
3, 4. Okay, so 0, 1, 2, 3, 4. So 1.24,
And then,
2.43, which is just shy of 2.5. So we got to take those away, right?
yeah,
Including 1.24. But we're not taking away 2.43
0.43,
because it's not in there.
yeah.
So the grand total goes from -3. Does it include 1.24?
It does not.
That's right, because we subtract that away. So it's this part. So -3 to 1.24 soft bracket
Mm-hmm. And
union.
then union
So or
2.43.
right.
And then I have a question as to how you write this, right? You could say 5.21 open bracket,
Yeah.
or you can say 5.21 closed bracket.
It cannot because it wasn't in this set to begin with.
Oh, excuse me. Sorry, I didn't mean to say that. I meant to say 5.2, like 5.2 closed bracket.
Ah,
Does it
that's
matter?
such a great question. That is a great question. This is when we get our microscope out. So you're suggesting we cannot include 5.21, right?
Yeah.
So maybe, but so 5.2 is somewhere really close. So let's get our magnifying glass out. And there's 5.2. See all that room in between there?
Hmm.
All these numbers 5.20001, 5.2 plus pi over a million, 5.2 plus, you know, 5.15, excuse me, 5.2105,
Hmm.
right? 5.2 halfway there, oh 05. There's an infinite number of real numbers in here that we are not allowed to throw away.
Okay, I got you. That makes sense.
So you got to just go all the way up to whatever this is, and then
And then exclude it.
because it was never there to begin with.
Makes perfect sense.
So use your magnifying glass.
Hmm. All right, cool. We can go to induction now. I just wanted to make sure that would I lose points if I did it on test, but yes, I would. If I
Okay, so let's move on to induction. What would you like to look at?
divisibility.
Well, yeah, we can do that. I want to ask, Shikemi, was it you or Rebecca? Was it you? Who was it that wanted to look at who was it? Or was it you, Elise? I just can't remember who it was. Is Elise even still here? I think we lost Elise. Tito, was it you?
It was me.
It was Rebecca. Okay. Rebecca, is there a particular induction problem that you either found in the back of the book or in WebAssign or in homework? Uh,
There
no.
wasn't a specific one, just like to make sure for like summation and then product. Like when you did that, I think it wasn't when you did it in class, I believe. I'm not sure.
So shall we look at homework number 9?
Yeah,
Because, I mean, that's a place to start, or we can go to WebAssign. If you look at the back of section 5.2 in WebAssign, I mean, in the book, there are lots and lots of questions. Do you all still realize that? Remember that very first homework number 1, where I asked you to kind of do an Easter egg hunt all over the place and look at the different materials, on the syllabus and on YouTube and in the ebook. And one of the questions I asked you to do was a particular problem in section 1.2 in the ebook, and I said, hey, did you notice that there are answers to the questions at the end of each section? And what do you think about that? Do you remember that homework problem that we looked at together or that we had? No? I don't know if you
I personally don't remember.
okay. All right. Well, let me just share my screen with y'all. And let's just poke around a little bit in the ebook because especially now that things are getting close to the wire for this course, it sure doesn't hurt to realize that the ebook is an excellent resource. Can everybody see my screen okay?
Yes.
So over here, I don't know exactly what your view looks like. I guess I can view this as a student and see. So I'll just say this course, but it's going to be the same for both of y'all. All right. All right. So hang on. Home. Let's go to the home. So it's assignments. Where's your, there we go. Here's the ebook. Okay. So click on your ebook. And if you don't see this particular menu, right, you can always find it. I'll show you how. Like if we go into the chapter on induction and you're actually in the text, it'll just kind of put you right back to wherever you exited the book next time you come in. So let's say you're not really where you want to be. See this little menu up here? Everybody see it? If you just click on that, it'll give you whatever chapter you're in, it'll give you a breakdown of all the stuff in that chapter. And we didn't do as much of this as I would have loved to. But anyway, we did 5.1, we did 5.2, and we did a couple of things from 5.3. So let's go to the exercise set 5.2. It's got lots and lots of problems. Let's look at number 3. This is a classic. It's the sum of the first imperfect squares. Shall we look at that one?
Yes, please.
You're in a noisy place, aren't you? I'm sorry.
Yeah, I'm in the library, so I'm gonna try to keep my talking to minimal.
So the library, is that noisy?
Yeah, like on the first floor they have like study rooms in like this one section, and there's like different cubicles, so there's like group work.
All right, so this is the ebook at the end of section 5.2. All right, so I'm going to stop sharing because I'm just going to lower this now and I'll stop sharing. All right, so this problem could be written with summation formula because this is a sum. This says it's the sum. We can use I. From I equals 1 to n, what's the expression for the term? What should I put here? 1 squared plus 2 squared plus 3 squared, keep on going up to plus n squared. Do you see that the term is just I squared? So that's the term. And it says that if we wanted to add those first n perfect squares up, the strictly positive ones, because 0 is a perfect square, but it doesn't add anything to the sum, that sum is given by this formula. All right. So let's just recall, in a proof by induction, we are going to, this is our P of n, and we're going to prove it for n greater than or equal to, well, the lowest value for n can't be less than 1, but it could be 1. So we'll just say for n greater than or equal to 1, okay? So we're just going to say let P of n be given as above, so we don't have to rewrite it. And now we'll start the basis. We want to get on the bottom step of our stairway to heaven. So we're going to let n naught equal 1. We're always told where to start. What do we wish to show? Anybody, not just Rebecca, she's in a noisy place. What do we wish to show in the basis steps? Anybody? Folks, you need to know this. We have the left-hand side of P of n, and we have the right-hand side. So does anybody know what we are trying to prove in the basis step?
P of 1 or
That's exactly right. So we're going to figure out what the left-hand side of P of 1 is. And we're going to figure out what the right-hand side of P of 1 is. And if we do it right, they should turn out to equal the same thing. Okay? So 1 is our value for n, okay? So it's the sum from I equals 1 to 1 of I squared. That's just that first term. It's just the first term. Because it says, oh, we're only adding up the one term, and it's just 1 squared. Just put the I squared, just put the 1 into I squared. So it's 1 squared, it's 1. Okay? Now let's take a look at the right-hand side of P of 1. We'll put a 1 in for n everywhere. So it's 1 times 1 plus 1 times 2 times 1 plus 1 over 6. Right? So it's 1 times 2 times, 2 plus 1 is 3 over 6. So 6 over 6, of course, is 1. So the left-hand side equals the right-hand side, and P of 1 is true. Or P of 1 holds. You can say it either way. So we got our basis. We are sitting or standing on that bottom step of our stairway. Let's look at the inductive step. What is the first thing we need to talk about in our inductive step? Anybody?
would it be P of K?
Yep, we want to talk about P of K. And since there's a variable involved, namely K, we tell our reader what K is first. Introduce K. So let K be some integer. It's not all integers, it's just some particular integer where K is greater than or equal to that bottom level value, 1. We assume our inductive hypothesis. Does everybody know what we assume in general? And then we'll write the specific statement for this predicate P of n. What do we always assume in the inductive step? We always assume we're standing on step K, right? And then what we wish is to show that we can step up. Okay, so we assume P of K is true. This is our inductive hypothesis, i.e., let's write exactly what we're assuming. All right, so I'm going to write it with summation notation. So N is now K. Our argument is K. So it's the sum from I equals 1 to K of still I squared. That's our left-hand side of P of K. What is it equal to? Somebody tell me what I should write on the right-hand side of P of K.
Would it be just K parentheses K plus 1 parentheses again 2K plus 1 over 6?
Perfect. Everybody understand that this is our money in the bank,
This is technically like
the inductive hypothesis.
we're just substituting, like we just proved the basis, so then now we could just like substitute K in for wherever N is.
That's right. We're assuming that we're standing right here.
Yeah.
We're assuming that, hey, we're on step K. It might be step 1. K could be 1, you know. We have to get off the bottom step 2 to step up to the second step, you know. But it could be up there at the millionth step, and we're just proving in general, if we're standing on some step, we will be able to step up to the next step. All right, that's our inductive hypothesis. Let's write our wish. It's pretty important to know where we're shooting, what we're shooting for. So we wish to show P of K plus 1 is true, right? I.e., we wish to show, now let's just go ahead and write P of K plus 1 so we know what we're trying to prove. And we can see P of K right here. I don't even need to see P of N anymore because we see P of K. So it's kind of the same idea. Instead of a K, here, 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 and here, we're going to now have a K plus 1. So we wish to show that the sum from I equals 1 to K plus 1 of I squared equals, okay, now somebody tell me what to write.
It'd be parentheses K plus 1.
Oh, thank you for those
The
parentheses.
binomial.
Yay, somebody's learned something.
And then it would be technically parentheses again,
Mm-hmm.
K plus 1. The K plus 1 plus 1.
Right.
And then you do 2 parentheses, yeah, parentheses 2. And then you put another parentheses K plus 1 plus 1. Yeah. Over 6, yeah.
Beautiful. And of course, this reduces. It becomes K plus 1 times K plus 2 times 2K plus 3. Okay. But we can just leave it like that for the moment because this is one of those problems where we're going to work on this side for a while. And then we're going to kind of be like, whew, as far as I feel like I can go. Then we're going to work on this side for a while and we'll meet in the middle. Okay. Does that sound like a plan?
That's good.
All right. So starting with the left-hand side of P of K plus 1. We're just going to see how far we can get with that. Okay, we're going to start with this. But we've learned all these nice skills. One of the important skills, Rebecca, that we learned and practiced before we really dug into induction was we learned how to break off the last term of a sum. And the reason we like to do that is, look, this sum goes from I equals 1 to K plus 1 of I squared. If you want to think about it in expanded form, this is really 1 squared plus 2 squared plus 3 squared plus keep on going plus we're stopping at k plus 1 squared. Do you see how these two are really the same thing?
Yeah.
Well, the point is our proof money says we know something about 1 squared plus 2 squared plus up to plus k squared. We know something about that. And then this last term, we could just break it off and have it sitting right there. Does addition care whether we add these up first and then add k plus 1 squared to it at the end? Doesn't care, right? So this is really the sum from I equals 1 to k of I squared. That's this bit plus the sum from I equals k plus 1 to k plus 1. It's just that broken off last term of I squared. See what I mean? You don't have to write this here. You could just write this here if you wanted. They're the same thing. This is just a single term where I has the value k plus 1 at the beginning and at the end. So it's just this term. Do you understand that?
Yeah.
And what a lot of students don't seem to understand initially is that the sum from I equals 1 to k, that's not just k squared. It's 1 squared plus 2 squared plus all the way up to and including plus k squared. See, this could be a gazillion. You know, this k could be 1,000. This could be 1,000 squares being added together. The point is we don't really know. It just could be 1. It just could be the 1 squared. Okay. Whatever it is, this is the abstract way to write it with a summation notation, or you could expand it. But the point is, why did we even do that? Why did we bother to break off this last term? Because we have this nice formula that tells us what this sum from I equal 1 to k of I squared is. It's equal to this, k times k plus 1 times 2k plus 1 over 6. That step is called using induction. By the inductive hypothesis or by induction, however you want to say it, it needs to be said to get full credit that right now, right here, we are taking the left-hand side of P of K and we're substituting in the right-hand side of P of K because we have assumed that the left-hand side and the right-hand side of P of K are actually equal. Does that make sense?
Yeah.
So let's make that substitution using induction and put that right-hand side of P of K in. And we still have this broken off term. This is by induction. This is just evaluating that. Okay. All right, well, let's just keep our wish in front of us so that we can get there, or at least as far as we can get. You know, we wish this. It's like our dream. You know, it's a wish. Okay, it's like a cloud. All right, so this is where we're at. We want this. Okay, so let's just compare and contrast. We have the sum of a fraction with a 6 on the bottom plus another term. What we're shooting for is a single quotient or fraction with a 6 on the bottom with a big product up top. So we've got to somehow combine these into a single fraction over 6. So what is our algebraic trick for doing that? It's called getting a common denominator, right? This k plus 1 squared is really over 1, even though we don't generally write the 1. The 1 is there. The common denominator from between 6 and 1 is just the 6. You know, when we add two fractions, we get a common denominator. It's 6. Well, the k times the k plus 1 times the 2k plus 1 is already over the 6, so we just bring that down and it's still over the 6, right? But in order to put k plus 1 squared over 6, what do we have to multiply by?
Six.
Thank you. Now, there are a couple of ways we can go. I prefer to factor rather than multiply all this stuff out if I can avoid multiplying it out, because if I multiplied all this out, I'm going to get a cubic. I'm going to get a 2k cubed, and I don't want to deal with that 2k cubed, So, but I realize I can see a common factor in this term that also appears as a factor in this term. What is the factor that is common to both of these that we can factor out of both this and this?
Would it be k plus 1?
It would indeed. Let's pull out that k plus 1. All right, so let's see what's left over from the first term. K times 2k plus 1 is what's left. You agree? Now, what's left from the second term after we factor out the k plus 1?
K plus 1.
Yep, there's a k plus
And
1
the 6.
and the 6. Thanks, Jonathan. And we're still sitting over 6, aren't we? So that's nice, because now we've got a single quotient. Do I need one more parentheses? I think I do. Can't watch myself right on the screen because then things get wonky. Somebody wants me. All right. At this stage of the game, let's look at let's take stock, okay? We're here. We want to get here, or at least meet in the middle. We're closer because the k plus 1 is a factor in both. Now, we still have some work to do, but we could go ahead and multiply this out. This is k plus 1 times 2k squared plus k plus 6k for a grand total of 7k, and then plus 6, right? Because 6 times 1 is 6. All right? Now, we're really not that far away, because if you can just think ahead, you can see that this is going to turn into k plus 1 times k plus 2 times 2k plus 3. Well, the k plus 2 and the 2k plus 3 are exactly the factors of this quadratic, 2k squared plus 7k plus 6. But let's just say you're not that great at factoring. So we can just stop right there. This is how far we got. Now, let's just start with the right-hand side and see if we can get it looking like that. It's a little easier. So the right-hand, see how we started with the left-hand side of P of k plus 1? It started out looking like this, and we got it all the way here. Now we're going to look at the right-hand side of P of k plus 1 is, or I'm going to write it exactly as it appears. So it's k plus 1 times k plus 1 plus 1 times 2 times the quantity k plus 1 over 6. Let's just start working on it. All right, so there's the k plus 1. This is a k plus 2. And this is 2k plus 2 plus 1. I think we can make the jump to 2k plus 3 without anybody losing any hair. If we can just get it looking like that, then we have met in the middle. Well, it is. Just multiply k plus 2 times 2k plus 3. K times 2k is 2k squared. Plus 3k plus 4k is 7k. And then, of course, 2 times 3 is 6. So now we got the left-hand side looking like, star, and the right-hand side looking like star. So the left-hand side equals the right-hand side, and P of k plus 1 holds true. You can just say holds, or you can say is true, or you can say holds true. So in fact, P of K did imply P of K plus 1 is true. We started with P of K. That was just our inductive hypothesis. That was a critical piece of information that allowed us to make the leap right after we broke off that last term. I apologize.
I have a question.
All right, let me just finish. We got one more thing to do, and then you can ask your question. What's the last step?
Invoke the PMI.
Yeah, let's invoke the PMI.
That was what I was gonna ask.
Yeah, we're not done yet. So now by the PMI, we can now say, and if you're in a hurry on the test, you can just say P of N is true. You don't even have to write what P of N actually is. You can just say P of N, because you already told me what P of N was at the beginning. For all n greater than or equal to, where did we start? What was our bottom level?
1.
1. And now that's a full credit proof. Other questions?
So I just have one more question, and it was in the social homework 9.
Uh-huh.
And can you do the second question?
Yeah, let me just make sure everybody's okay with this one before we move on.
Alright.
Does anybody need to see more on this one? Or are we good to go? All right, so this was page 7 of our notes. All right, let's move on then. All right, special homework number 9. What problem number, please?
2.
So this is such a pretty little problem. That was the very first one. It says that the sum from I equals 1 to n of the terms of this arithmetic sequence. This is an arithmetic sequence that's missing the term a naught. When I is 1, it's like we started at -4 and we just keep adding copies of 5. It is what this is. It's an arithmetic sequence if you started mixing at 1. Anyway, it says if you add up the terms of that sequence, it's n times 5n minus 3 over 2, excuse me. So was there anything in particular about this problem that was causing you issues? Like what is it that stumped you with this one?
Like, I don't even know how to explain it.
Was it doing the induction step?
Yeah.
All right, I want to show everybody now what you can do if tomorrow you're working an induction problem, and my golly, that P of K to P of K plus 1, it seems impossible. Okay, so let me just show you uh, uh, a strategy to maximize your points. Okay, because I don't know how strong your algebra skills are. I want you to get most of the points by just showing you understand the sort of what has to be done in order to prove the statement, even if you can't actually do every little detail. Okay. You can indicate where missing algebra should be. But if you can tell me at least how to get things started by assuming P of K and breaking off the K plus first term, if it's that sort of problem, and then say, I don't know what the algebra is, Dr. Good, like a little arrow, but then say, this is what I know I want to get, and show me, the right-hand side of P of K plus 1, and then go ahead and invoke the principle of mathematical induction, you're going to get a lot of points. So this is P of N. and it's true for n greater than or equal to 1. So our n naught is 1. Let P of n be above. And do we need to do the basis, or are you good with the basis?
Can we just go over it, please?
We certainly can. What's the first statement that we need to make when we start the basis? We need to tell the reader
What
what,
and not?
yeah, what the bottom step is. So just say let or assume or suppose and not equals whatever it is. You'll always be told what it is, okay? You're never going to have to guess where to start. You can always be told that. All right? So what do we wish to show? You tell me our wish just so we know we're on the same page. We want to show that this P of n is true when n is 1. So we wish to show P of 1 is true. Does that make sense? This alone gets you a point or two, okay? Now, it always helps if it is a formula type situation. It always helps to know that there's, a left-hand side of an equation and there's a right-hand side. It can help kind of organize your thinking, okay? So let's look at the left-hand side of P of 1. What is the left-hand side of P of 1? Can you tell me? It's Stephen that's asking, right?
Yeah.
Okay. So let's take a look at the left-hand side of P of n, and let's just put a 1 in where we see an n. So it's the sum from what?
1,
I equals 1 to what?
1,
Good. Of.
5i minus 4.
Nicely done. And what does that evaluate to?
And, 1. Do we still use the,
We're going to use I equals 1, but the I is right here.
mm-hmm,
So we're going to put the 1 in here.
mm-hmm. So it was going to be 5 times 1 minus 4.
So what is 5 times 1 minus 4?
1.
Great. Perfect. So now let's evaluate the right-hand side when n is 1, okay?
Mm-hmm.
And just tell your reader what you're doing, and it helps you organize your thoughts too. It's worth the time. So what is the right-hand side of P of 1? It is what?
And
So what
so
is n though?
1.
So
So
1,
1, 5 times 1 minus 3 all over 2.
great. So it's 1 times 5 minus 3 over 2, right?
Mm-hmm.
So what is 5 minus 3?
2.
So what's 1 times 2?
2. So 2 over 2 and 1.
All right. So the left-hand side equals the right-hand side, and P of 1 holds, right?
Mm-hmm.
All right, we got the basis done. Let's realize now that go ahead and, give me a space or two, give yourself a little breath. And now we're going to start the inductive step. This is where we assume we're on step K and we want to step up to step K plus 1. Okay? So we have to talk about K. Let K greater than or equal to 1 be some integer. It's not all integers. It's just some particular but unknown integer that's at least 1. Okay?
Mm-hmm. Mm-hmm.
We're going to assume, well, what do we assume?
P of K.
P of K. Because what we have to do is we have to assume we're standing on step K. We wish, we're going to try to show you're right, but we assume P of K. Let's go ahead and write down exactly what we're assuming. All right, you help me. Because now, instead of P of N, we're just going to start putting a K everywhere we used to see an N. All right, is this still in focus? All right, here we go. All right, so we assume what?
Oh, yeah,
The
so it's
sum.
I equals to the sum. I equals 1 to K,
Good.
5, I minus 4.
Exactly. We keep the i's, in the
And just
expression.
mhm,
All right.
goes to K, 5K minus 3,
Uh-huh.
all over 2.
This is worth points right here. I mean, every step you can take in the right direction is good points. And I do like to put a box around my inductive hypothesis because otherwise I sometimes get confused between what I have in my hand to work with and what I wish. Let's go ahead and write our wish. And now we don't need to see this anymore because we can see P of K. So what do we wish to show?
So P of K, no, P, K plus 1.
Nice. I.e., let's write exactly what our wish is. That means everywhere we see a K now, we're going to replace it with the
K
argument.
plus 1.
Yeah, man.
K plus 1. 5I minus 4.
And
It goes to K plus 1.
we need a parentheses around that K plus 1 because we're replacing a monomial with a binomial.
5K plus 1.
Times K plus 1, it requires parentheses.
Minus 3
Uh-huh.
over 2.
Okay. This is a wish.
Mhm.
I don't want to confuse it with what I know I have. So I'm just going to just use that to help remind myself. I want to prove this. I can't start with this, but we're going to get to use that. All right. So here we go. It's the same kind of deal as before. We're going to start with the left-hand side, use the tools and strategies that we have learned to break it up so we can use this inductive hypothesis and substitute. And then we're going to try to turn it eventually into this. We'll get as far as we can. But it may not necessarily be easy to get to here. So one of the ways that makes it easier is if we just go as far as we can with this. Wherever we get, we can just say that's as far as I can get without making a mistake. Then we back up and then we look at this and see how we can start changing it. And maybe we can meet in the middle. Does that make sense?
Mhm.
Okay, here we go. Let your reader know what you're doing. Starting with the left-hand side of what? What if-
The inductive,
Okay, we know this, okay, but that's not what we want to prove something about.
oh,
We want to start with this.
all right.
We're going to start with this and turn it into that. Does that make sense? So we're starting with the left-hand side of P of K plus 1. I know it's a little bit against intuition, right? But we're just starting with the expression. Nothing wrong with just saying, oh, we're looking at the sum from I equals 1 to K plus 1 of 5I minus 4. All right, so what is the thing that we should do now? Remember, we'd like to use this money, but we can only use this if we either see this, and we're nowhere close to that, or we see this, and we're not that far away from seeing the sum from I equals 1 to K. We got more than that here. What is our kind of, algebra trick or tool that we use to rewrite this sum from I equals 1 to K plus 1? This is an important step. If you can't, do this breaking off the K plus first term, you're going to have some trouble. Do you know what this really means? What this sum is? Let's just take a look. Let's expand it. All right, when I is 1, this is 5 times 1 minus 4. Okay, that's the first term in this sum. Plus, right now, put in 2 for I. So then what is the next term? Stephen?
2.
Well, it's the next term
Mm.
is when I is 2. So it's 5
Oh.
times
2. Yeah.
minus the 4.
Mm.
Plus, just keep on going. The term right before the term when I equals this upper limit, k plus 1, would be when I is k, right? Because k comes right before k plus 1.
Yeah.
So the penultimate term would be 5 times k minus 4 plus, and then the last term is when I is k plus 1. So it's 5 times k plus 1 minus 4. So this closed form of the sum of the first k plus 1 terms is really this. Does that make sense? Now, this is term A1. This is term A2. This is the term A sub k.
Base of K plus 1.
See it?
Mm.
That's what this really represents. This is just the closed form of this expanded form. Okay? So the bottom line is we have information about the sum from I equals 1 to k of 5i minus 4. We have information about from A1 plus A2 plus AK. See, we know something about that sum. We know it's equal to that by our inductive hypothesis. So right now, we can milk that by breaking off the last term of this sum. This k plus first term doesn't have to be rolled in with these. We can split this one off. This is the sum from I equals 1 to k of AI, but AI is 5i minus 4. You see, that's the expression for a sub I, plus this broken off term. You could just go ahead and write it. Just go ahead and evaluate that last term. You know, this is the a sub k plus 1 term. See what I mean? So you got to understand that when it's a formula involving a sum or a product, you want to start with the left-hand side of p of k plus 1 and break off the k plus first term. I think we need to move on. Now, because we did that, we suddenly see the sum from I equals 1 to k. We're suddenly looking at A1 plus A2 plus up to A sub k. Well, we know what that sum is. That sum is equal to this. That's what we were able to assume. So now we're going to make that substitution, which is our inductive step. It's where we actually use the inductive hypothesis by the inductive hypothesis. You know, so you can just say by induction, but if it helps you, you can say by the inductive hypothesis. We're going to make the substitution. What should we put in for this now, Stephen?
So, do we put in the K 5K minus 3 all over 2?
Exactly. Now you're starting to have earned a lot of credit. Like if you can do that, if you can break off that last term, do this and evaluate that last term, right? This is really
Can
5.
you explain that last part you just do one more time?
How we got from here to here?
Yes.
Look at what we have assumed. P of k says this sum from I equals 1 to k, which is right there, which is really, these added together, is equal. We got to assume something.
Mhm.
We got to assume that that sum is equal to this. In other words, we got to assume the formula works for k.
Okay.
If we couldn't get anywhere, if we couldn't assume that we're standing on step k, see, we got to assume that, and
Yeah.
then we wish to step up. So that's why I always put a green box around my P of K to remind myself this is money in the bank that I got to spend this, and we're spending it right here.
Yeah.
The moment we spend that, that
So
is
you
where,
assume P of K, you're just
like,
that's just
right? You're like, well, wait a minute, why can we assume P of K? Right? You're
mhm.
like, how come we get to assume that, right?
Yeah.
Well, because assuming that we're standing on some step in the staircase isn't a big deal. We already know we actually are standing on the bottom step. We already got on the step, you know, 1.
Yeah.
So we know we're standing on some step. Like if nothing else, we're definitely standing on step 1. So we assume we're standing on some step K, could be 1. But the point is, if we're standing on any step K, and we prove that that's enough to bounce us up to step K plus 1, then we're proving that we can get on the staircase and climb it. Which means that this statement P of n will be true no matter how large n gets.
Okay.
Does that make sense?
Yeah.
Yeah, we get to assume something. Like you don't just like prove stuff out of thin air. You gotta have a hypothesis. All right. So now let's just say you get that far and you have no clue how to get from this to what you're shooting for, right? I'm here to tell you this is the way to maximize your points. You can just say, oh my gosh, I'm here. I know I'm trying to get to the right-hand side of P of k plus 1, right? Because we wanted to change the left-hand side into the right-hand side, but I have no clue or I'm running out of time. I don't know how to do it. So just do this, folks. To lose at most a fifth of the points on the problem. At most. Just do this. Algebra, help Dr. Good. I don't know how to do it, but show me you know what you're trying to get to. See what I mean? Do you
In this particular case, one of the things that I found helpful, as I was just trying to work this out just now, I got to the step. Um, let's see where. Well, so I multiplied out some things. Let me see. So
Jonathan,
we need some
you're
stuff
getting ready
2
to
over
tell
2.
me that you know how to do the algebra and that you have a quick way to do it. Can we come to that in just a sec? And I will write down exactly how you do it. Let me just finish this and then we'll go back and you can tell me exactly how to do it the easy way. Would you do that for me?
Yeah, sure.
Okay, great. Because I just want to finish this for the folks, but we will finish it. All right. Say, I don't know how. Okay, but you will show us how in just a minute. I don't know how, but the point is, for everybody else in the room who doesn't, necessarily understand induction as well as you'd like to, do you realize where we are trying to get? Anybody besides Jonathan? We started with the left hand. See, this is our wish to show this equals that. We started with this on the left. What are we trying to reach? Anybody?
The right-hand side of PK plus 1.
Yeah, we're trying to get to k plus 1 times 5 times the quantity k plus 1, whole thing minus 3 over 2. Just realize where you're trying to get to. If you can show me that you do know we're shooting for that, you're not going to lose that many points for the missing algebra, okay? And then just say by the PMI. Don't forget, invoke the PMI for those last point or two. Point, 1 or 2 points. By the PMI, we can say P of n, whatever the statement is, or if you're out of time, just say P of n is true for all integers. Go ahead and tell me where it starts. In here it was 1, sometimes it's 2, sometimes it's 0. Okay, so now, Jonathan, C star below, do tell what the easiest way is that you have found to get from this line down to here. I am all ears. Can I write down what we've got there? And
Yeah,
you're gonna
sure.
walk me through that process. I'm loving it. All right.
I'm certainly going to try to.
All right, did you like having the 5K plus 1 here, or did you prefer to have it 5K plus 1 minus 4?
I actually left it as 5K plus 1 minus 4.
Let's do that, because you know what? That is fine too. All right,
Um,
what do we do?
and what I said to myself is, all right, I need to do that step we had in the last one that looked kind of like this. I've got a fraction on the left, and I don't have a fraction on the right. So I'm just going to multiply that thing on the right by 2 over 2. And you can simplify rewriting this by just, put a 2 in front of that whole thing in parentheses. Exactly so.
Oh, great.
All right, so then the next thing I did was I simplified that crazy business on the right. So I just said that ends up equaling 2 times 5K plus 1. All the rest stays the same.
Yeah, because 5K plus 5 minus 4 is definitely 5K plus 1. Folks, notice how even though we're only really working on this, I am bothering to write the whole thing down. You're not doing yourself any favors by saying that this equals, and then you're just working on that. Go ahead and write it all down. Okay, now what, Jonathan?
So the next bit, I'm going to multiply out basically the stuff that I've got on the top. So I'm going to say 5K squared minus 3K plus 10K plus 2, all over 2. And now I'm in a position where I can simplify that numerator a little bit more and say the middle term is just going to be 7K. And at this point, I got stuck for a second. I said, well, all right, what do I do? There's got to be some way to get to that craziness. But I said to myself, all right, well, even though I can't rely on that explicitly, I could maybe do some scratch work and figure out how to get there by working backwards. So I took that thing that we're trying to get to, and I just started multiplying it out. I said, all right, well, if I've got, let's see, K plus 1 times, the big thing, 5K plus 1 minus 3 as the numerator.
Yeah,
Then
do the numerator here over the side, not in here. Yeah.
Mm-hmm. Then I can simplify the bit inside and say it's 5K plus 5 minus 3. Keep the K plus 1 the same. Then I can simplify that to 5K plus 2. Thanks for following the implicit bit that I'm doing there. And then I just multiplied that through, and I could tell I was getting close at that point. 5K squared plus 2K plus 5K plus 2, and then simplify the 2K plus 5K to 7K. And then I've got the numerator I want.
And you can work backwards from here to get to there.
Exactly. So what I did is I just wrote those steps in reverse. So let that be done.
Keep going.
Mm-hmm.
To get to the left-hand side. Because this is this is the numerator, left-hand side, but this is all over 2. Now, see, we're writing true statements. This is the numerator, right?
Mm-hmm.
Thank you, Jonathan.
Yeah. It was a scrappy one, so I was glad I was able to figure it out.
Everybody following that? You can do some scrap work, not in here, folks, but like on a piece of scrap paper, get it sorted out, and then work, just take these steps backwards to get to. Ta-da. Hey, Abdul.
Hmm?
How are you?
Good, how are you?
It's good to see you, or at least hear you.
Yeah. I don't have a camera, but
Don't worry about it, neither am I. If you can see, I got my robe on here. All right, folks. It is 10:22. Rebecca, do you feel a little better about mathematical induction?
Yeah, I do.
So go back and maybe any of those homework 9 problems, that you weren't really feeling great about, go ahead and, try them again. You can sneak a peek if you need to, right? But
Hmm.
again, folks, you don't need to die on the algebra sword. Yeah, if you got time and you can take a deep breath and do this, then you got a way because you can get there by working backwards, and then meeting in the middle. But you can always, in a pinch, just say algebra help, but indicate that you know exactly where you're going. The right hand side. Oh, did I put left hand side? We're shooting for the right hand side. Sorry. We want the right hand side. My bad. But anyway, yeah, we're right hand side of P of K plus 1 because we started with the left hand side up here. And then invokes the PMI. You can get most of your points. Be able to break off the term, be able to use the inductive hypothesis to substitute, and then that's B territory right there, folks. Okay. And then any extra steps you can get, just get you further. It is 10:24. Right. So I took like a 6-minute break. So, we've been at this for about 2.25 hours. And I really do need to call it a day. I'm so glad everybody came. Before I call it a day, I'm going to take a picture of these notes. It'll take about an hour for this video to process because it's very long. That would have been an advantage of me just stopping it. But it still doesn't start the process until the meeting closes. But anyway, I'll get this stuff up. It'll be up by midnight. And quiz 6 is already up. The solutions are up. Hey, check for typos. Check it for typos. You might get some points. I might have made a typo. I did it in a rush. All right.
Thanks a bunch for hanging out, especially, late at night. It's very generous of you to have the bonus pop-up office hour.
Well, thank you for saying that.
yeah, thank you.
I'm so glad to see so many people here. And just tell your buddies and friends and pals that take this class with me in the future to come to office hours from the beginning. Right? Like, do me a favor. If you're going to put the word out on social media that you hate my guts, I don't care. But just drop people the word that go to office hours. Get your questions answered. Have a great night, everybody. Thank you for playing.
Thank you, you too.
Good
Thank you,
night.
Dr. Good.
Good night.
Thank you, Dr. Good.
Good night. You're welcome so much.
Wow.
So glad you made it. Stephen, I'm glad you made it.
All right, thank you. I was just writing my last notes down. All right,
I
see you
know,
tomorrow.
and I'm trying to get this in order because,
Because there's a lot of papers.
yeah, I think I accidentally labeled 2 papers, page 6. Oh, but this is the real page 6, I think, because then we went to the ebook to induction.
Yeah,
All right, so I'll just have to go page 4, page 3. We got like 10 pages of notes.
it was a
Page
lot. We've been here for like 2
2,
hours and 30 minutes.
page 1. Okay, so yeah, because we took that little break between
Yeah.
this page 6 on set differences, right? Y'all were talking about that. And then we started on induction. So this is actually page 7. I'm going to stop recording.